Greetings and welcome, internet friends. Mr. Waddy by himself today in a large empty room, but here I am reviewing for the Systems of Equations test, and so I'm going to go over a couple problems for you. So hope you enjoy. So question 6 from the review says solve the system by substitution. And now technically I could solve this by graphing. I could solve it by elimination, but we're going to use this particular method. And so step 1 in substitution is to solve one of the equations for one of its variables. So I've got x, y in the first equation, y, x in the second equation. And as I'm looking at these, the best choice is to solve for a variable that has a positive 1 coefficient, right? Which usually that 1 would not be written. If I wanted to say solve for this y, I'd end up at some point having to divide by 3, which division has the potential of making fractions, and fractions usually make a problem a little bit harder. So to solve this equation for y, I'm going to subtract 3x from both sides. I end up with y equals negative 3x plus 6. I'm a fan of slope-intercept form, writing my variables first. So here is the end of step 1, right? I solved this equation for one of its variables. Here we go. Now, the thought is this, that if these two things are in fact equal, I can exchange them at any time I'd like. And so step 2 is I substitute this in for, in this case, this is one of the only times it matters, the other equations y, all right, is what I end up doing. So step 2, I'm going to have something like this, 2x plus 3, and instead of y, I definitely need parentheses here, so I remember to distribute. Instead of y, I'm going to have negative 3x plus 6. Let's center that equal sign a tad, shall we? Right there. So now, in order to solve this equation's, yes, I agree, uglier than either of the original. However, it's got one thing going for it. There's only one kind of variable, and we know how to solve for that. So I'm going to distribute, combine like terms, simplify, and solve. So I've got 2x minus 9x plus 18 equals 4. I can combine some like terms. I've got 2x and negative 9x combining to be negative 7x plus 18 equals 4. Subtract 18 from both sides. And right, I'm just doing the classic chapter 1 inverse operation stuff in order to solve for this variable. And let's see, x is being multiplied by negative 7, so the inverse is division. Divide both sides by negative 7, I get x equals 2. So that is only half of my answer, however. So the next thing I need to do, I've got to find y. The solution of a system is going to be the xy combination that makes both of them true simultaneously. And so I do substitution again. And technically I could plug this in for this x or this x, but tell you what, the best place is always going to be the end of step 1, because notice this equation's already solved for the other variable that I'm looking for. So I've got y equals negative 3, and instead of x, I'm plugging in 2. And this one, because it's already solved, I just pretty much have to PEMDAS it, order of operations. So y equals negative 6 plus 6, y equals 0. So my solution is x equals 2, y equals 0. If you want, you could write that as an ordered pair, 2 comma 0, because remember, the solution of a system is going to represent the ordered pair that is the intersection of those two lines if I graphed them. So this is the substitution method, right? Solve for one of the variables, plug it in, solve again, plug it in, bam, go, go, go. All right. Trickier but more powerful method is the elimination method. And so what I'm going to do here, the idea is that I want to add these equations together and have it so that one of these variables, the x's or the y's, eliminate one another. And right now if I do that, 8x and 6x is 14x. Negative 7y, negative 5y would be negative 12y. They don't eliminate. And what I need to do to have them eliminate is to have these variables, these coefficients of the variables, be opposites of each other. And to do that, I've got to figure out what's the least common multiple between 8 and 6. So 8 and 6 both go into 24. Now, I could have said 48, but that would be a common multiple. It still could work for me. It just would be larger numbers. And between 7 and 5, I get 35. And so when I'm looking at these two things, I'm going to choose the smaller one, because small numbers are usually easier. So the question is, step 1, yeah, we haven't even started the first step yet. Step 1 of the elimination method is to multiply one or both of the equations by a number, a constant, that will give me opposite coefficients. And so I'm going to multiply this equation by the thing that's going to give me a 24. So 8 times what is 24? I believe that is 3. So I'm going to multiply this entire equation by 3. And similarly, I'm going to multiply 6x by the thing that's going to give me 24. And 6 times what is 24? That's 4. Now remember, I want these to be opposite coefficients. Technically, yes, there's a way to have them be the same and just subtract the equations, but I'm a fan of addition, so I'm going to go for opposites first. And it doesn't matter, I just need one of these to be negative, because since both of these terms were positive, I don't want to have 24x and 24x. So let's multiply through. So 3 times 8x is 24x, 3 times negative 7y is negative 21y, 3 times negative 3 is negative 9. Make sure you remember to multiply the right-hand side. Negative 4 times 6x, there's a negative 24x. Those are those opposite coefficients I was looking for. Negative 4 times negative 5 is plus 20y, equals negative 4 times negative 1 is positive 4. So step 1 is now done. I've multiplied one, or in this case, both equations by a constant in order to get opposite coefficients. And this makes way for step 2, in which now I add these together. And notice the benefit here is that these terms fully cancel out. Negative 21y plus 20y is negative 1y, or negative y. Negative 9 and 4 combine to be negative 5. And now I can just solve this opposite both sides is the easiest way. Sometimes solving that, I think, is called step 3. But step 4, now I've got half of my answer. Remember, just like I did up here, my answer is going to be two values for x and y. So I'm going to still need to find x. And one of the ways I can do that is by substituting this into either of the equations y's. And I'm going to select the second equation because 6, 5, and 1 are smaller than 8, 7, and 3. That's my only reason. It'll still work just fine if you plug it in to the other one. So 8x minus 5 times y, which I've just solved for, and y is equal to 5 is the claim. Let's try to make it look a little bit nicer. So let's solve this. 8x minus 25 equals negative 1. We'll add 25 to both sides. Wonderful. 8x equals negative 24. And then divide both sides by 8. And I get x equals negative 3. So my solution for this system is negative 3 comma 5. And remember, that represents the intersection of these lines. That's what these equations represented, okay? So that's the elimination method. This is, yes, at times more complicated because you got to set it up just right, but once you do, it's oh so sweet when one of your variables eliminates. Okay, this is for solving. This is actually a weird use at times. It's not as powerful right now for us, but it will end up being very helpful when I'm trying to solve algebraic problems with a single variable that maybe I don't have the skills of solving. This is actually an interesting way to do it. Solving by graphing, this is, I'll emphasize that this is single variable. And the route that I take here is, now I've already kind of reworked this a little bit, yeah, this one specifically, to get it in a more familiar form for us. But what we do is I take each side of this equation and set it equal to y. So I'm essentially introducing a variable that wasn't even part of the problem originally. And the reason I'm going to do this is that maybe I'd have a hard time solving algebraically. And instead, I'm going to solve now graphically. where I might be able to graph these two things. Maybe I end up using some technology to do so, and it will then tell me where the intersections are, and I'll be able to work it back towards a solution for x, or solutions, as sometimes is the case. Now, these are absolute value equations, and the form that I'm thinking of for absolute value is y equals a abs x minus h plus k, where a is going to determine the slopes of the sides of my absolute value v graph. H and k will represent the coordinates of the vertex. So looking at this, I can see that a for this first graph is 2, and a for this graph is an invisible 1 on the outside, right? So 1. I can see that h here is the opposite of the number next to the x, so that's -4. And, oh, typo, here we go. 5, there we go. Yikes. Ha. So let's see, so h is going to equal a -5 in this instance. And for both of these, there was no k value. There's no number being added on the outside, so you could think k equals 0, if you want. So to graph these, let's graph the blue one first. So I'm going to start at h comma k, so that's -4 comma 0, and I'm going to move by my slope, which is up 2 over 1, up 2 over 1, up 2 over 1, up 2, right 1, right? I'm always moving to the right. That's the way Mario moves. Typically. And absolute value graphs are this V shape where they're mirrored over themselves over the axis of symmetry that passes through the vertex. So I can also go up to backwards 1, or to the left, up to backwards 1, up to backwards 1. Let's see if I can get my line tool here. So I'm going to draw this absolute value graph, right? You guys could use a ruler or the edge of a note card or something like that to make your graph look oh so sweet. I recommend lining up your points with points that are kind of further from each other rather than nearer. It'll decrease, you know, kind of a wrong slope for your line. It'll more likely hit the points you meant. So there's the first one. Let's graph the purple graph. So -5 comma 0. Oh wow, these are real close to each other. Ooh. Huh. Yeah, these are really close. I wonder if I might have made a mistake right here. Looks like I might have. That's fine. Yeah. You know what? I think this was supposed to be a minus sign. Right there. Let's see. Yeah, I think so. So I think this would have been plus, because this would have been minus. Let's see if Mr. Waddy can do this trick real quick. If I select this, how sweet would this be? I don't want the vertex there. Oh, no, you didn't. Look at that. Look at that. Classy. Right there. Gorgeous. So yeah, so I think that's where it was supposed to be. My apologies. And this one is at, right, -5, 0. And the slope is 1, so up 1 over 1, up 1 over 1, up 1 over 1, etc., and up 1 backwards 1 for my V graph there. And so I'll line this up. I've got my vertex at the bottom of the V. Ooh. And I might not have enough space for this graph. Because I have a feeling this graph is getting further away than that one. Here's one intersection, but it looks like these two would hit at some point. So maybe I'll have to change the size of the graph at some point. So my solution ends up being where the graphs intersect. So that's the point 1, 6. But remember, the original problem here only had x's in it. So I actually don't care about this y value. So I'm going to say x equals 1 is one of my solutions. And tell you what, let me open up a quick Desmos. All right, so I'm going to have y equals, oh dear, y equals abs. You can fast forward if you need to, 2x minus 8. Yeah, I definitely did that I definitely messed that one up at one point. So, so notice here's my Desmos graph, very similar to what I have, same solution there, but I just needed to zoom out a little bit more, and I can see there's another solution at 1318 is where that other solution is. So if 1318 is another solution, just the x coordinate is of interest to me. So x equals 1 or x equals 13 is what I'm going for. All right, thanks. Let's see, one more problem if you're interested. If you have time, obviously you got a test today. Let's see, if I want to graph this system of inequalities, so this is not an equal sign, these are less than signs. I'm going to put both of these in slope-intercept form by solving for y. Remember with inequalities that if you are going to multiply or divide by a negative at any point, you have to flip that inequality. But this one looks like it won't be a problem. So I'm going to put both of these in slope-intercept form. So I'm going to have y is greater than negative 1/3 x plus 2. That there be one of them. And over here, I'm going to subtract 2x from both sides. Those are not like terms. Notice one's got a variable, the t'other doesn't. And I'll have y is less than negative 2x plus 7. Let's see, for the sake of this video getting long, I'm going to graph these a little bit speedier. So let's see, this one's got a y-intercept at 2 and a slope of negative third. So down 1 over 3, down 1 over 3, down 1 over 3. Now this is a greater than sign, so that means it does not equal to the line. It's going to only go up to the line but not include it. And so graphically in 2 dimensions, the way we represent that is with a dashed line. Okay, so instead of having a solid line, it's going to be dashed. Similar to back in the day when we were graphing on a number line, we'd have open circle or closed circle, right? Closed circle is if it included an equal part. And it looks like similarly here, I've got a y-intercept at 7 and a slope of negative 2, down 2 over 1, down 2 over 1, down 2 over 1. And this one also does not have the equal part, so it is also going to be a dashed line. And then that's not going to be all. It's not just a matter of the lines, but it's also these are either greater than or less than. So we're going to have to shade these as well. So let's figure out the shading on these. So this one is a less than sign, less than in a y perspective. Y is our vertical up-down variable. Less than would be below the line. So let's see. So this one's going to look something like this. All right, I'll color this in. There we go. Something like that. All right, and for the blue graph, this was y is greater than. So greater than is going to be shaded above this blue line. And so that's going to look something like this. And so the solutions of the system are going to be points that happen to land in the common shaded area. So like this point here, this point here, this point here. So that means negative 2, 5, the coordinates of that point. If I plug them in for x and y, and for both of these, it will be true for both of them. Obviously, points over here are not solutions. So if I plug in 9 and negative 5 for x and y, it will not work for either. But a little bit interesting is the fact that if I plug a point in here, it will work for my blue equation, but not the purple. And if I plug the coordinates of a point from here, this whole region, it will work for the purple equation, but not the blue. All right, well, thanks for watching, internet friends. Best of skill on your test today. Adios.